for today. We're going to continue our discussion on this effective stress. As I mentioned last time, effective stress is a very important concept in geotechnical engineering. So I'm going to spend quite a few lectures, and I've prepared a number of examples for this chapter. And just as a brief review of what we covered last Friday. So last Friday, I introduced this concept of effective stress and also this effective stress equation. So if you look at this slide here, this highlighted equation, sigma prime equals to sigma minus u, that's the effective stress equation. So basically, effective stress is the difference between total stress and pore pressure. Okay, so that's the equation we're going to use today to calculate stress along depths for a given soil profile. Okay, and the other thing we covered last time is basically given this soil profile, if we know the unit weight of soil, how do we calculate total stress and how do we obtain effective stress? I used this very simple example, this profile here, where the water pressure, the water table is put at the ground surface. So this is a very simple case. And for this case, actually, if you look at the last equation here, effective stress, gamma saturate times H minus gamma water times H. And if you factor out H, so this last expression becomes basically the difference between two unit weights. One is the saturated unit weight, one is the unit weight of water times H. And this, these two terms within this parenthesis, this is actually the definition of buoyant unit weight. Okay. And we call this gamma sub B here, subscript B, or sometimes people use gamma prime for buoyant unit weight. Okay. So this gives us another way to calculate sigma prime. If it's below water table, you can use the buoyant unit weight times depth to calculate a sigma prime. Okay, so that's a kind of a special case. This is only for saturated soil. All right, so that's where we stopped last time. And for today, so I want to start from this profile here. So the first thing I want to talk about today is this, it's a very generic soil profile. And I want to use this to show basically how do you calculate stress variation along depth. Okay, so the setup is we are given this soil profile, the ground surface. Okay. So we have the ground surface. And this time I put the water table some distance below the ground surface. So this is perhaps a more general, more common case. So water table, and this is water table. Okay. And also we're going to look at different soil profiles, different soil layers basically. So I'm going to assign different unit weights to different layers. Okay. Above ground water table, I'm going to assign this moist unit weight I call gamma M1. So this is a moist unit weight of soil above water table. And sometimes people like to use dry unit weight for water, but more often the natural soil is moist, even if it's above water table. So I use gamma M1. And for these two soil layers, H1 and H2 and H3, so I call the unit weight gamma saturated 1 and gamma saturated 2. Okay. So these are basically two soil layers below the water table, and the unit weights are saturated 1 and saturated 2. Okay, so that's the setup. So use this generic profile, I'm going to calculate total stress, pore pressure, and effective stress. So that's total. This is pore pressure. And last one is effective stress along depths. Okay, so I'm going to calculate these three stresses along depths. And to do that, we'll start with the total stress one. So total stress, basically total weight times the depth over unit weight. And you're going to use for moist soil, you use the moist unit weight. I'm going to put it right here. So at this interface, the value of total stress at this depth is gamma M1 H1. Okay. So just unit weight times depth. So that's total stress at depth H1. And then at the next interface, so let me put it here. So at this depth, the total stress, again, total weight above this point over the cross-sectional area. And the result of that is basically gamma M1 H1. Okay. So that's a contribution from layer 1, that moist soil layer, plus the saturated unit weight gamma SAT1 H2. Right. So again, that's gamma M1 times H1. So that's the first layer. And then gamma saturated 1 times H2. So that's the unit weight of the second layer times its depth, H2. Okay. So that's the total stress value at this location. And finally, that last point, okay, at the bottom of this soil profile, then the total weight, so we have gamma M1 H1, first layer, plus gamma saturated 1 H2. Okay. And then you have the weight of the third layer over its cross-sectional area. So that gives the unit weight of the third layer times its depth. So plus gamma SAT2 H3. Okay. So that's the total stress value at the bottom of this soil profile. Okay. And then in between, you can use simply linear interpolation. So I can connect all these dots to get a variation. So this profile, stress profile. So this is straight line to connect these. Okay. So that is the variation of total stress along depth. Okay. So that's sigma. And again, if you look at these interface values, we're using the unit weight times the corresponding depth of that layer to get total stress. So that's how you calculate total stress. If it's a moist layer, you use moist unit weight times H. If it's a saturated unit layer, you use saturated times depth. Okay. So that's the total stress. And then pore pressure. So pore pressure is pretty simple. It's basically unit weight of water times the height of water column. Okay. And for the first layer, so this moist layer, because it's above water table, so it's going to be 0 and 0 here. Okay. Above water table, the pore water pressure U is 0. So that's pretty simple. Then below water table is basically unit weight of water times depth. Okay. So at, say, depth H2, it's gamma water times H2. So that's the unit weight of water times H2. And then for the bottom of the soil profile, we have gamma water times H2 plus H3. Okay. So the pore pressure at the bottom of the soil profile is unit weight of water times the total height of the water column. So that's from this location to the water table. So H2 plus H3. And then you can connect these interface points to get the variation, that profile. Okay, so we just use straight line to connect these points. Okay. So that is the profile of pore pressure along depth. And finally, this effective stress is simply the difference between these two. So this is sigma minus U. Okay. So this first point, okay, this is gamma M1 H1. Okay. So that's the value of basically effective stress, it's the same as total because pore pressure is 0. And then for this point here, for this point we have gamma M1 H1 plus gamma saturated 2 H2 minus the unit weight, the pore pressure, gamma WH2. Okay. So that's the pore pressure at this, excuse me, the effective stress at this location. Just the difference between these previous two stresses. And then the last one, so it's gamma M1 H1 plus gamma saturated 1 H2 plus gamma saturated 2 H3, then minus the pore pressure. Okay. And then you can connect connect points to get the profile along depths. So this is the effective stress variation along depths. The first one, the pore pressure is 0. So you're subtracting basically 0. Below this ground surface. And then above this water table, the pore pressure is 0. Okay. So the pore pressure only exists below water table. So you have 0 pore pressure in this moist soil layer. So this is basically the effective stress profile. So one thing I want to mention here. So for this saturated soil layer, basically for these two locations. Okay. So if you look at this expression here, this effective stress expression, so we have gamma moist times H1. Then the next two terms, you can factor out H2. So that's the depth of the saturated soil layer 1, then multiply by the buoyant unit weight. Okay, so this is So this is what I showed at the beginning of this lecture. If the soil is saturated, the effective stress for that soil layer can be calculated using the buoyant unit weight. So that's this second term. Okay. So this is basically the effective stress of this second, that is the saturated soil layer. Okay. Gamma B, let's call this gamma B. Actually, there's a typo here, excuse me. So this is gamma saturated 1. So let me remove this. Sorry. Okay. So this is gamma B1. Okay. So gamma B1 is a buoyant unit weight of that this saturated soil layer. And then same for the this last point here, the point at the bottom. You can again use the buoyant unit weight to calculate saturate effective stress. So this is gamma M1 H1. So that's the first layer, the moist soil layer. Then the second soil layer is a saturated soil layer. So we can use buoyant unit weight. So let me call this gamma B1 times H2. And then the third layer is also a saturated soil layer. So we can use the buoyant unit weight of that layer, gamma B2 times H3. So this is the effective, this is another way to calculate effective stress. Again, for this saturated soil layer, you can use the buoyant unit weight. So this is okay. That's the difference between saturated unit weight and unit weight of water. This is a very generic case. I'm not plugging in any numbers. I'm just using gamma M, gamma saturated for unit weight of soil. So next I want to show one example. I'm going to go over the first example. It's basically a layered soil profile. And instead of using these symbols, we're going to plug in numbers. So I'm going to plug in unit weight numbers to calculate these stresses. Okay, all right. So next I want to talk about a few key points in stress calculations. So first, for total stress calculation. For total stress, if you're calculating the total stress above water table, you want to use gamma moist, gamma M for moist soil. Or if it's a completely dry soil layer, you want to use gamma dry, gamma D, just as our example one. So that's for total stress. So you use the corresponding unit weight times the depth of that layer. Okay. And for below water table, you always use gamma saturated to find the total stress. Okay. So it's always gamma saturated times the corresponding depth. Okay. So this is total stress sigma. And then there's a special case where you have water above ground surface. Okay, so this is a case, say, if you have a lake, you have a river, and you want to estimate the stress. So example is a lake or river. Okay. For both cases, you have water above the ground surface, basically. And if you want to find out the stress in the soil mass, and you have to account for water in total stress calculation. So gamma water. So gamma water acts for total stress, meaning you need to add the weight of water above ground in your total stress calculation. So one example, so let me give you one example. Okay. So let's say you have soil and water is right here. Okay. So say this is the bottom of a lake. You have water body above your ground surface. So soil, and this is water. In this case, say the depth is 10 feet and 10 feet here as well. And just to make the calculation easier, I'm going to assume saturated unit weight is 100 pounds per cubic foot, just to make the calculation simpler. Okay. So let's say in this case, you have soil below the water table. So this is say a lake. Okay. And then your total stress, sigma. So at the bottom of the lake, you have stress value there as well. So that value is gamma water times the depth of this soil, this lake. So gamma water. So this is, so use pound per square foot. So that's the basically at the bottom of the soil layer. Say at the bottom of the soil profile, your total stress is 624 plus 10 feet of saturated soil. Okay. Again, you need to add that weight of water into your total stress calculation. So this is 1624 PSF. So that's the total stress. Again, you need to account for the weight of water in your total stress calculation if that water body is above the ground surface. Okay. Right. So this is total stress. And in this case, just for completeness, say for pore water pressure. So water pressure is basically this linear variation over depth. So that's 624. And here it's 20 times gamma water. Okay. And then the effective stress is the difference between these two. At the bottom of the lake, effective stress, if you take the difference between total and pore pressure, this value is 0. Okay. And that makes sense because you don't have any soil above ground surface. And effective stress by definition is soil particle-to-particle contact force per area. So if you don't have soil, of course you don't have effective stress. And then at the bottom of this soil profile, effective stress value is the difference between total and pore pressure. Okay, so that's 1624 minus 1248 and 376 and 0 at the water surface. Okay. All right. So that is total stress, and that is a very special case when you have water table above ground surface. Okay. So again, you need to account for the weight of water in total stress calculation. Right. So that's some keys in finding total stress. And then for pore pressure and effective stress, okay, some keys in finding pore water pressure. The first case is we have water with free surface. Okay. So you have free surface water. And let's say you have sand layer, and this is ground surface. Okay. So if you have a free surface, and then say this is, you put a standpipe here, a piezometer or standpipe to measure pore pressure. Water is going to rise up to this free surface. Okay. So this is a pretty common case. You have free surface, and let's call this depth capital H. So in this case, let's call this point A. Okay. So the pore pressure at point A, if you have a free surface, is simply the height of this water table times the unit weight of water. Okay. So basically distance from that point to the free surface of water table times unit weight of water. Okay. So that's the first case. In the second case, it's a little bit tricky. This is artesian condition. So in artesian condition, let me put soil profile. So we have ground surface again. It's called ground surface. Okay. And this time we have different soil layers. So we have sand layer, clay layer, and another sand layer. So sand, we know sand layers are basically permeable layers because sand is a very permeable material. So we covered this in chapter 7, permeability. So we know sand has high permeability, so it's permeable layer. But clay is impermeable layer. So we know the permeability of clays is very, very small. So it's considered impermeable layer. Okay. In this case, this sand layer at the bottom actually is under artesian condition. Because it has an impermeable layer, that clay layer pressing on top. Okay. So it increases the pore pressure within that sand, the second sand layer. Okay. And the top one has that free surface. So in this case, let's look at a few points in this soil layer, soil profile. So consider the first point, point A. So point A is at the bottom of the first sand layer. Okay. In this case, if we put a piezometer here, a standpipe, water is going to rise up to the free surface. And let's call these steps H1. I'm going to call this H2 actually. Then a few more points. So point C. Okay. It's at the top of the second sand layer or at the bottom of the clay layer. Okay, so this is I call point C. Okay. So for point C, if you put a piezometer here, if I put a standpipe to measure the pore pressure at C, okay. Because it's under this artesian condition, it's being pressed by that impermeable clay layer, the water is actually going to rise above the free surface. So then the water pressure, so at point A, is simply gamma water times H2. Okay. And this is also called, this is hydrostatic pore pressure. So this is under hydrostatic. Okay. So in contrast to the artesian condition, so hydrostatic pressure. Okay. And then pore pressure at C, gamma water times H1. Okay, so this is artesian pressure. Okay. So C, this is pore pressure at C. And then if you want to calculate, let's say, let me add another point. Point B at the middle of the clay layer. And if you want to estimate the pore pressure at point B at the middle of the clay layer, so you can use simply interpolation. So if you know A and C, you can just use linear interpolation. Okay. So that's how you estimate pore pressure in the middle of clay layer. Just use interpolation. All right, so this is some basic notes in finding pore pressure. And last one, some keys in finding effective stress. Okay. So for effective stress, also have a couple points here. The first is you can always use that effective stress equation to find effective stress. Okay. So you can always use this sigma prime equals to sigma minus u. So this always applies. Okay. If you can find total stress, you can find pore pressure, you know effective stress. So this is always true. And then the second point here, that this is the buoyant unit weight I mentioned earlier. If your soil is below water table, okay. And also if the water pressure is hydrostatic, okay. So hydrostatic meaning it's not artesian pressure, it's not under that artesian condition. Okay. If both conditions are met, then you can use buoyant unit weight to find effective stress. Okay. One can use the buoyant unit weight. And this buoyant unit weight gamma B or gamma prime equals to saturated minus water, gamma water. Okay. So sigma prime okay. So you can use this to find the effective stress. And this H here is the okay. So basically the thickness of the saturated layer. But if you want to use this point unit weight, you need to make sure that the soil first is below water table, it's fully saturated, and two, the pore pressure is hydrostatic, so you don't have artesian condition. Otherwise, you have to use this effective stress equation to calculate effective stress. Okay, all right. I think this is a good point to stop, actually. And what's coming are basic examples. So I prepared a number of examples to calculate effective stress, total stress, pore pressure along depths. And I'll go over that in the next lecture.